So just let me introduce a bit the team that is behind this service and system evolution for the Black Sea physics. We are basically an heterogeneous group that covers all the major thematic aspects that may then enable us to deliver the products to you all as users, so through CMEMS. So we have a management board that is in charge for organizing the activities on the evolutions and the operations part for the Black Sea area. We are composed in a development team that is much more in charge for the evolution of the product from the scientific point of view. And close to it, there is an operational team that is devoted to guarantee the high reliability of the service and so the maintenance of the products that then are delivered and go online through the CMEMS web portal. And then we have an advisory board that specifically target and drive us towards the scientific challenges and the operational, targets that we are continuously improving and developing for making the Black Sea products state-of-the-art and close to the user needs. As previously introduced by Fabrice, the Black Sea physics, the Black Sea MFC, so the Monitoring and Forecasting Center, joined the younger, let's say, component in the CMEMS umbrella, and we are in particular focused in this presentation on the physical products, so on describing basically the products that we provide and that are able to describe the ocean state and the dynamics in the Black Sea basin. So our capacity is to provide everyday analysis, so the best estimate of the ocean state in the Black Sea, as well as forecast overall a period of 10 days. And together with the near real-time, these near real-time products, we deliver also the multi-year products, so the reanalysis that provides a retrospective data records for the recent years in the Black Sea basin. These kind of products should be able to satisfy somehow the different user needs that goes from monitoring towards planning for the future evolution of downstream services, for example. So in this context, the offer is basically devoted to reach this target and the capability of and the usability of these products for developing new services in the Black Sea basin. So through the CMEMS web portal, in particular for the physical products, you may access two kinds of products family: the near real time that provides analysis and forecast for the essential variables in the Black Sea, so temperature, salinity, currents, mixed layer depth, and the sea surface height. And together with the near real-time products, we developed the multi-year catalog that provides over a long period from 1992 to 2018 the reconstruction of the ocean climate in the Black Sea. And basically, we provide the same kind of variables, essential variables, to help to support the monitoring in the Black Sea area. How this is possible? I mean, how the product is prepared for the final delivery. Basically, to make it possible, we integrate several components in the modeling framework. So we access external upstream data that are basically the data, the observations, and the atmospheric forcing that we need in order to make the model running and ready to provide our final products, so our analysis or forecast. Then we have a modeling system that is based on a numerical model that reconstructs the hydrodynamics in the Black Sea at regional scale, together online coupled with a data simulation model that takes the observations and corrects our model estimation in order to be as much as possible somehow high quality and close to the real, let's say, the real ocean. And both systems that are interconnected are used to serve the operational side. So thanks to this integrated system, we may build the operational framework. So we basically deliver the products. But at the same time, our aim is also based to improve the quality of the products itself. So we have a service evolution and product quality component that mutually in two ways interact with the modeling framework and with in order to improve the operational products. Going into much more into details, the Black Sea near real-time system, so the system that make possible to have analysis and forecast, is based on NEMO ocean model, and that is a circulation modeling system that solves the Navier-Stokes equations in a spatial grid of 3 kilometers of resolution in horizontal and 31 vertical levels. This system, this model is coupled with a data simulation scheme that is able to assimilate satellite and in-situ products that will be described later by the other colleagues in the CMEMS framework. And in order to allow the model to prepare to integrate the physical variables in the Black Sea basin, we use the atmospheric forcing CMWF state-of-the-art resolution at 12.5 kilometers to drive the sea interaction, so to make the surface conditions on the top of the basin level at the surface. We assimilate through the data simulation scheme mainly three kinds of products, of observations product: the sea level anomaly from CMEMS sea level TAC, the sea surface temperature from the SST TAC, and the vertical profiles for temperature and salinity that are provided by the in-situ TAC within CMEMS. The Bosphorus here is our, let's say, tricky point, is a very challenge point from the modeling perspective. Our basin is, from the modeling point of view, closed at the Bosphorus Strait. So the Bosphorus works like a sort of inverse river in order to provide the proper freshwater balance at the surface. And regarding the rivers that are flowing into the Black Sea, we are considering a total number of 72 rivers distributed along the Black Sea coastlines, whose values in terms of discharge are provided by the SESAME project database. The products are delivered through the web portal, and we provide also information about the quality, while at regional level in our consortium, we also developed the capability to provide operationally some specific daily bulletin and evaluation skills related to our operational products. The processing system in the Black Sea is organized in a chain that runs every day and over two kind of different level of quality. We have a daily cycle that runs every day, of course, and provides 3 days of analysis, 1 day of simulation, and 10 days of forecast. And once a week, we run a long analysis cycle that covers 14 days. The idea behind this strategy is to improve the best estimate for our forecast cycle through a data simulation that during the 15 days before the running day collects the higher quality and the huge number of observations that have been collected in the Black Sea, so the system is able to assimilate them and to provide a better estimation of the ocean state in the Black Sea. The forecasting period so covers 10 days in total for all the data sets, except the hour limits that are provided just for 5 days as a forecast period. And if once accessed the CMEMS web portal, you can basically select the available variables that are subdivided as daily and hourly data set for the 3D temperature, salinity, and currents, and 2D sea surface height, mixed layer depth, and bottom temperature. Together with the access to the net CDF file, so to the datasets, we provide also 2 reference documents. One is the product user manual that contains the description of the processing system and the technical details about the product and the datasets, and the quality information document that instead provides information about the quality, the statistics, and so an evaluation from the scientific point of view about the product that we deliver. Through our regional website maintained by CNCC, we have also the publication of daily bulletins about the statistics of the major variables that are considered useful for diagnose the quality of our products. So in this picture we have, for example, the statistics for the sea surface sea surface height, so the accuracy of our product with respect to this sea level data that are delivered as a product, as a satellite product in CMEMS. So we can see that the accuracy of our model is about 2.3 centimeter compared to the available sea level tracks. And similar statistics are also provided for temperature and salinity. Here in particular we compare the model output, so our analysis, against the temperature and salinity profile at different depth in order to measure basically the quality that our system reaches at prescribed layers. So in this case we can see at 80 meters and at 30 meters how the daily, the seasonal cycle of the temperature is represented by the system, and what are the major errors that we have as well as the evolution of the error during the period that we are observing in this time series that spans from 2018, and it is updated every day. And we can see also the distribution of the observations that we assimilated that are represented in this map. Going to the end, some few words about the multi-year modeling system that is basically similar to the near real time, except the fact that this system, this model that provides our reanalysis is forced by CMWF ERA interim atmospheric forcing and assimilates basically the reprocessed data from CMEMS tags, so for SST, sea level, and in-situ data. If we go to see in our CMEMS catalog what is the offer, basically we provide, as for the near real-time system, also for the reanalysis, the daily data sets, and in this case we have also the monthly data sets provided for the whole period spanning from 1992 to 2018, and as well as the technical and scientific documentation that describes the general characteristics of our system. I cannot see any more my slides. I guess that sorry.
We will recover it.
But regarding the multi-year system, In particular, CMEMS offers also the possibility to provide okay, this is for the waves, sorry. The multi-year system provides also another two important information that could be relevant for the users to know and to use, that are related, one more related on the scientific perspective, that is the ocean state report, that provides contribution about sea surface salinity anomaly, salinity trend, and subsurface temperature anomaly in the Black Sea over the period 1993 to 2017, and it is annually updated as ocean monitor indicators. That is the second output provided also by the CMEMS through the CMEMS web portal. In this case, we have a picture of the physical, in this case, of the temperature anomalies in the Black Sea towards the period 1993 to 2017, in order to monitor the major physical features that are developed through the long period in the Black Sea. In this case, for example, it is nice to see that the model is able to capture the cold intermediate layer that has been observed also in reality through the observation in 2012.
1 minute, Stefania, sorry.
Yes, I go towards the last slide, that it is much more on the evolution. So basically our intention is to continue to improve and evolve our system. So we plan to increase the vertical resolution in our near real-time and as well multi-year system towards 121 vertical levels, keeping the modeling framework as a state-of-the-art, so towards the new version of the model. The Bosphorus Strait will be considered and will be implemented as an open boundary condition, and of course more upgrades will be provided also in the data assimilation framework to make the system able to assimilate new observations that are collected in the Black Sea. And finally, we among the list of the major revisions that we are performing in this period, of course, the bathymetry is another point that we are improving in order to make the model able to and ready to the next steps that are devoted to improve the representation of the physical features and dynamics in the Black Sea basin. Thank you.
Okay, thank you, Stefania. We have time for one question, which I see also in the chat, and it is if you plan to include the Sea of Azov in the forecast for the Black Sea.
Yes, in the sense that in our plan, in our 3-6-year plans, the idea is to include the Azov Sea. The Azov is very tricky, is very important from the modeling point of view, because this is a source of ice. So the evolution will follow also what is done in the modeling framework, in particular in NEMO, to be able to run the ice modeling component in regional seas. So in the future, we would, of course, extend. The intention is to include the Azov as well, and with this additional improvement that is related on the representation of the ice.
Okay, thank you very much, Stefania. Thanks. And so now we pass to
Okay, sorry, it seems we lost Paola. So I will I will let the floor to Joanna for the Black Sea waves presentation.
Thank you at the beginning, Paola, and now for Boris. I activated it, so it shouldn't be a problem. So being a part of the Black Sea CMEMS consortium, we at HZG are responsible and provide information and also data for the waves. So let me first introduce who we are. The Helmholtz-Zentrum BS.PHY is a part of the Helmholtz Association in Germany. The map here shows the distribution of the Helmholtz Research Institutes, and our institute is located in the northern part in BS.PHY, which is near Hamburg, at the Elbe River, and has at about 900 employees. The Helmholtz Association contributes to solving grand challenges facing society, science, and the industry. The Institute for Coastal Research has three major directions: the Biogeochemistry and Coastal Seas Division, Ocean System, System Analysis, and Modeling. Research is focused on regional and coastal processes. Our department, Hydrodynamics and Data Assimilation, is under System Analysis and Modeling Division, and our research focus on waves and ocean modeling, coupling between models and data assimilation. Let me very briefly introduce our Black Sea MFC teams responsible for the waves production. Arno Behrens, he's now also attending the meeting, and he will be involved in question and answers. He's our wave modelers. He's actually the one who is developing and maintaining the wave model since several decades now, and he's responsible for the smoothly operation of the waves forecast and providing also the multi-year products, wave climate, model ensembles, and also the data assimilation. Gerd Geier is the one who is responsible for the product quality of our products of waves, validating them with satellite data, and also responsible for providing the documentation. Marcel Ricker recently joined our group, and he's still a PhD student working on ocean drift modeling, but also waves and circulation modeling, and he's involved in quality control and service evolution. I am a head of the department, Hydrodynamics and Data Assimilation, and I am the PI for the project, and I'm doing ocean modeling and coupled model system analysis, extreme events, and also work on ocean predictability and the variability. Let's go back to the Black Sea MFC waves product, and here this is a brief overview of our waves product, similar to the physics. Actually, we produce two kinds of products, the near real-time products and the multi-year products. The more information about the data and also about the models, of course, can be downloaded from the Copernicus CMEMS web portal. And regarding the near real-time products, what is very important here to notice is that we produce hourly data, which are actually not average, but they are instantaneous one. The products are available from 2017 ongoing, and they are updated daily. Regarding the multi-year products, they are from the period of 2002 until December 2018. And these products also are 1 hourly output data for 17 state variables that I will present you later on. The model that we use is the Wave Model 1. The Wave Model 1 is the one which is developed and maintained in our department. And actually, this is an open source model, and the model can be obtained freely, or also you can ask Arno Behrens for the latest version of the model. The state-of-the-art model is suitable tool for simulating ocean wind waves at global, regional, but also at coastal scales. The one actually runs successfully at many institutions worldwide for operational and scientific and climate purposes. The wave model solves the energy density balance equations in the direction frequency space. The two-dimensional energy density is calculated at each model grid point. And the model has different options, which actually the users can activate for their simulations. For example, they are shallow or deep water, wave breaking, data simulation, or for coupling with ocean time-dependent depth, and also depth current refractions. For CMEMS, the model provides daily net CDF files, including 1 hourly outputs for integrated wave parameters, which actually are calculated from the two-dimensional spectra information provided by the model. And here I present a schematic workflow of the wave productions. The atmospheric forcing that we use is similar to the one for the physics, and it is taken from the CMWF at 180 degrees horizontal resolution. The model grid is 3 kilometers, and also the bathymetry is consistent with the one of the physics, which is also very important for the forthcoming activities related to coupling between the physics and waves and providing future products which are based on the coupled models. The model version that we use now is 4.6, and for the Black Sea, we include the shallow water, depth refraction, and wave breaking parameterization. And we use a directional resolution of 15 degrees and 30 frequency bands. In respect to in-situ observations, however, the Black Sea is extremely poor of existing systematic wave data to be used for product quality control. Therefore, the validation of our products is mainly done with the recently available satellite data, also through CMEMS portal. For assessing the quality of our products, we use all available satellite altimetry over the Black Sea, namely Sentinel-3, JSON, Cryosat, and Saral Altika. For example, the pattern on the left-hand side shows the model simulated significant wave high, and it can be seen that the maximum is on the west-southern part of the basin, and the minimum in the eastern part. And if you hardly can see the line on the western part, this is the along track distribution of the significant wave high provided by the Saral Altika. And also validations for the along track satellite information is shown for the Saral Altika and also for the Cryosat. And the red dots are the model simulations, the blue one are the satellite data, and one can see that there is a good agreement between the simulated significant wave high and long track observations. And a bit of more statistics and the validation. Here, the validation is shown as an early statistics as called QQ diagrams for 2017 as an example against JSON-3 and 2018 against Sentinel-3A. And on the top, you can see actually the different statistics. Again, I refer to the documentation in the CMEMS portals in which you can find also the equations, how these statistics have been estimated. And what is seen is that actually the model is fit well with the observation. So, and we get actually a bias of minus 1.7 centimeter for 2017 compared to JSON, and minus 3 centimeters compared to the Sentinel, but also much more statistical analysis can be found in the different products. We also perform automatic validation of our near real-time products, and we use the satellite data, which are all these satellite data that are available, and the validation program runs every day and actually provides statistics which includes important parameters, and they are continuously actually checked, and in this way we are able to monitor and continuously also check the quality of our wave model results. And this validation starts every day for each month, and normally they stop at the day of the last month, and statistical tables are also available at monthly basis. And here this is just a schematic presentation of this automatic validation in which the model simulations are used together with automatic download and post-processing of the satellite data, and we are just mixing them and then providing this monthly validations. And just an example here, this is a table with the statistics for March 2020, and you can see that there is information of the different statistics like mean, bias, regression, and so on. And you can also see the information of the satellite data that have been used for those validations. As I mentioned, also in addition to the near real-time products, we provide also the multi-year products. And here, this is an illustration of the variability and of the model simulations compared to the satellite observations. And the figure here also demonstrates not only how they fit models and data together, but also what is the variability based on the different analyses of the significant wave height. For example, the median, mean, and maximum significant wave height, but also the different percentiles. The red line corresponds to the model, the blue dots are the observations. And what is clearly seen here is that for the median and mean, the variability is similar to the lower percentiles, while for the maximum significant wave height, it is actually similar to the higher percentiles. And the model and observations fit well, especially in the last decades of the period. And there are some discrepancies in the beginning of the JSON-1 observations. And another example Stephanie also mentioned is providing the ocean monitoring index. And for the waves, we provide the 99th percentile significant wave height and the anomaly. And here the plots show the average annual 99th percentile of the significant wave height, which demonstrate the typical feature for the Black Sea with maximum of the western part and minimum in the eastern part. But the other patterns demonstrate what is the anomaly of the annual 99th percentile of 2019 in respect to the average. And what can be seen that for 2019, we have a positive anomaly in the southwestern part, but also along the eastern coast, and the negative one is on the western shelf and also in the eastern part of the Black Sea. And as I already mentioned, we provide information of the 17 integrated wave parameters. So the wave model is not only significant wave height, although we use this for validation and assessing against the satellite observations. But in addition to that, you can find the information from the different periods and also the information of the different direction, but also primary and secondary swell outputs provided by the wave model, as well as, for example, the Stokes drift components, which are also very important, for example, for oil drift or any kind of drift estimates in reflex of the question that was during the first session. So you can actually have this information for the Stokes drift and also combine it with waves and circulation information for any kind of user cases which are related to drift estimates. As I already mentioned, more information about the products, about the model setups can be found in the quality information documents and also in the product user manual documents available into the Copernicus site. Information regarding also the wave model is there, but if you have any specific questions, you can always contact CMEMS users desk, or you can contact the model developers of some specific technical questions related to the models. And the same is for the multi-year product. And we are working towards improving, something happens. We are working towards improving our products, and we will upgrade our system with using the state-of-the-art wave model 1, which is the cycle 6, which includes the new physics and also the novel diagnostics. The bathymetry of the next products will be also adjusted to the one of the physics. Data assimilation is included in the multi-year products. So for the whole multi-year product data set, we will assimilate satellite data. And what is also very important, especially for the waves product, is that we will switch to the hourly atmospheric forcing. And also we will consider the wave-ocean interaction processes for the future products. So that's it. Thank you very much.
Thank you. Thank you, Joanna. We have some question for you just about this one. Where can we find the WAM cycle 4.6? Is it an internal version? The latest version I can see online is a WAM cycle 4.5.3.
Yes, version 4.6 as well as version 6 is still not freely available, but as you can see from my slide number, I think it was number 5, you can always contact Arno Behrens and ask for the latest version.
Okay, thank you, Joanna. For all the attendees, the questions are recorded during the webinar, and we will put all the questions and the answers on the chat platform during the round 2. Thank you, Joanna.
Thank you.
Paola,
I'm back.
You're back.
I'm fully back. Sorry, there was a technical problem, I guess. Okay, thank you, Joanna. And we pass now to the remote sensing observation products part of the presentation. These are divided in two. So there will be two presenters, one for the sea level, one for the ocean color. The first one is Binka Rosmorduk from CLS France.
Hello.
Yeah.
I'm Binka Rosmorduk from the Sea Level TAC. I'm going to present you the sea level remote sensing observation product. So now we are not anymore in the modeling, we are in satellite observations. I'm working at CLS, which is a subsidiary of the French Space Agency, and we've been working on altimetry remote sensing, so the measurement of sea level, for the past 27 years or so. So I'm going to give you a brief idea of what are sea level and satellite altimetry, of the parameters which are in the product grouped under the name of sea level, and also the product which are in the CMEMS catalog. So satellite altimetry and sea level, what are we talking about? So you've got this quite messy scheme, and I'll detail a bit each things within. The sea level measured by satellite are measured by an altimeter. The altimeters are available on different satellites. You've heard about JSON and Sentinel-3 in the previous presentation, for example, but there are other ones. The altimeter is measuring, in fact, the difference between the difference between the satellites and the surface. So this is satellite to surface distance, my gray line here. So this rough line is the sea, the surface of the sea. On the satellites, you've got other measurements which are measuring the altitude of the satellite. And the main point is then to do a subtraction to be able to measure the sea surface height. So you've got different references used. Altimetry usually used an ellipsoid. The ellipsoid is a geometrical shape of the Earth. Not a sphere, but slightly bump at the equator. You've got the absolute dynamic topography, which is a sea surface height with respect to the ellipsoids. If you are a sonographer or modeler, you'll probably are calling this sea surface height dot. But this is sea surface height with respect to the geoid. The geoid being the Earth gravity field, well, the shape of the ocean due only to the Earth gravity field. So you've got, there are also bumps and troughs within this geoid. And what's mostly used here are the sea level anomalies. The sea level anomalies are whatever is changing, the variable part of the sea surface height. And in fact, it's a sea surface height with respect to a mean sea surface. So those are the words you'll find back and back in the altimetry vocabulary. Sometimes you will find sea surface height anomalies instead of sea level anomalies, or sea surface height instead of absolute dynamic topography. But whatever, those are the main quantities you'll find. All are distances. So, however, this is not as simple as that. I'm sorry. You've got also a number of corrections happening either on the surface, on the instrument, or in between in the atmosphere. So, in fact, we are correcting a lot of things to compute the sea surface height with respect to whatever you want, but you need to take into account a number of corrections. The most evident are tides, because tides are changing the height of the ocean. So if you don't take them into account, you'll be measuring mostly tides, which can be your study, but which may not be your study. So a number of corrections are used to be able to compute a precise sea surface height. And my last point is maybe strange for you, but the sea level and satellite altimetry do not provide with images. Basically, the altimetry data are measured just beneath the satellite, so you've got only a thin thread of data and a lot of blank in between. The whole point of the data we provide are to fill in the blank. So, for example, this is a map provided by 4 satellites during 3 days. So you see, you've got a lot of data, but a lot of blank spaces here and there. So don't be surprised for the data not to be grids. You have grids, but those are processed data. And for now, this is because you'll have in 2 years a new satellite which should provide with imagery. So the parameters in the product, you've got the sea surface height anomaly or sea level anomalies, meaning the sea surface height with respect to a several-year mean, which provide you with the ocean variability. You also have the derived geostrophic current, the current computed from the surface slope. So those derived from the sea surface 8 anomalies only provide you with current variability. And in the product, you'll find also the sea surface absolute 8, or ADT, or sea surface 8 with respect to the geoid. But note that for the Black Sea, they are not yet available because the reference surface is currently being computed. The mean dynamic topography, which is things with a quantity we are adding to the anomaly to have the absolute 8. And if you don't have this absolute 8, you don't have the derived current. So those are not yet available over the Black Sea. They are available almost everywhere else, in open ocean, in the Mediterranean, but you won't have yet it over the Black Sea. And now you've got those parameters within the product, and then you've got two different products, the gridded sea level maps, which are highly processed from all the satellites available on a given day and a little time before, possibly after if we are not in real time. The idea is to use optimal interpolation to fill in the area where we don't have the measurement for the day or for the past days. And we also have a long track sea surface 8, which are by satellites. You will have only the thin thread of data I was showing you earlier. So for those data, you'll have different kind of data, and if you are trying to do the Jupyter notebooks, you'll find a notebook for each of the products. So the second product may seem complicated, but it can be very useful because you can uncorrect it from a number of things like tides. And also, if you're modeling, you may not want to take into account the interpolation we are using to make the grid. You may want to use your own interpolation within your model. So for the Black Sea, note that you must use the European area. So how to find those products? Those products, either you go in CMEMS website in About Us and About Producer, where you will find a sea level thematic assembly center box explaining the center of the production center, and there you will have an overview of all the sea level from satellite products. Or you can go into the Marine Copernicus service catalog, click on Ocean Products, and the quickest way to find the satellite sea level products is to search for sea level without a blank, without a space in the middle, and then you'll have the old list, including some old products. For example, you've got an old product for the Black Sea, which is no more updated. So that's why I was mentioning you should use the European product for the Black Sea, because the old Black Sea product won't be updated anymore. So I hope you'll try it. You'll try yourself on those products, and I hope you'll enjoy and find them useful. Thank you.
Thank you as well, Binka. And before the question on this remote sensing part, I pass the floor also to Vittorio, so he will also present you the ocean color products. So Vittorio is the senior researcher at the National Research Council of Italy. And as I said, he will present the ocean color satellite observation products for the Black Sea. You have to switch your microphone. Vittoria, you had to switch on the microphone, which is one of the two buttons in your...
Sorry, here I am. Sorry, couldn't find the button. Apologies. So I was saying good morning, everyone. I'm going to introduce you to the Ocean Color satellite products for the Black Sea. So within as you know, and you've been told by now, within CMEMS there are 7 modeling center and 7 and 8 thematic assembly center, one of them in Ocean Color, and in this moment we serve 181 products across the regional seas and the global ocean. Of those, the important for you is the chlorophyll product, which is the phytoplankton chlorophyll concentration, and is one product that serves both what in Ocean Color jargon are called case 1 and case 2 products, being the bluer waters, the open ocean, and the optically complex water close to the coast and the shelf. In terms of optics, we serve the remote sensing reflectance, RRS, a series of inherent optical properties, the vertical attenuation of the water column at 490 nanometers, the Secchi depth, the PAR or the suspended matter. Each of the products, not all products are served in each basin. As for the rest of CMEMS, the products are operationally available in 2 processing levels, Level 3 as daily composite products, single or multi-sensor, and as Level 4, daily interpolated or weekly, monthly composites. We have near real-time and delayed time that are normally produced within a day or within a month, and then the REP being the consistently reprocessed time series, which is produced every 6 months or a year and is a full reprocessing or an extension of the reprocessing time series. As I said, we covered the whole basins, and I'm focusing now onwards on the Black Sea. For each of the products in each of the regions, the products are based on regional algorithms to improve their quality locally at basin level. And each of the product types are checked for quality through dedication validation analysis, and these are, for instance, some of the examples of the matchup analysis which are contained in the quiz, which are the quality information documents. As a snapshot of what is the product evolution, and I'm going to go directly from the product evolution of these 3 years, our main focus has been to introduce the Sentinel-3A OLCI data stream, and we've done that already since a couple of years. We will be introducing the Sentinel-3B and the VIRS NOAA data as well. And we've been paying particular attention in improving the chlorophyll accuracy for shelf and coastal waters, and we introduced, in fact, last year, a new updated algorithm for the Black Sea. We will, and that's more of importance, introduce the full resolution OLCI ocean color data at 300 meters by the end of the year. So as I said, in the Black Sea, we introduced in the last couple of years the Sentinel-3A OLCI as single sensor, and we introduced the Sentinel-3 OLCI in the multi-sensor processing chain, and we introduced a new algorithm for both OLCI and algorithm, and I'm going to provide some details on these improvements in the next couple of minutes. So few of you may be familiar with our production center, and in the processing chain, we have the same processing chain for most of the production of the Mediterranean and Black Sea. So the examples are based on the Mediterranean to show what we do. But what I want to show briefly is that the near real time and the REP time series production are similar at the end level. So once the level 3 are produced in remote sensing reflectance, the same geophysical products are there. The near real time, we produce we produce in realm based on the data sources being the level 2 from the space agencies, while the level 3 in this moment are based on the Ocean Color CCI initiative run by ESA, where they have their own processing chain, and we adopt it as our own upstream. The important point to make is that because we serve a multi-sensor product, and this is an example you see in blue, the aqua overpass in blue, in red the EVIRS overpass, and in green where both of them are there, so where there is both of them is with both the sensor were there, and for those we have to merge the remote sensing reflectances before being able to apply a chlorophyll algorithm. No, I'm pushing the wrong button, apologies. This means that for each of the basins, we have their own algorithms. In this case, this one is the one for Mediterranean, which is not our interest. But what I want to show is that the effect of the basin coverage for the Mediterranean Sea and the Black Sea, the coverage is really similar, is that if you see each of the different color lines are the different sensors as how they contribute for the cover, but the important is that we, by using 2 or 3 sensors, we have a gain of 20% on average, which is the cyan line. By adding OLCI in 2019, we have an extra 10% of coverage, so we reach coverage of 70 to 80% for the basin on a daily basis. This is the first validation dedicated to the Black Sea, and for the Black Sea, we can do the validation of the remote sensing reflectance using the Aeronet OC sites that are available in coastal waters in the coastal waters of the European part of the basin. And overall, we show that the reflectance is rather accurate for the multi-sensor product, and as expected for most of Ocean Color products, there is highest inaccuracies, highest mismatch in the extreme blue band at 412 nanometers, and in the red band at 600 nanometers, particularly for the low values. Now let's come to the product development. So the new algorithm that we introduced for chlorophyll in the Black Sea. The algorithm is based on 2 different regional algorithms. One is a band ratio that is aimed to work mostly in the open part of the basin, and the second one is a multi-layer perceptrons, being a neural network, which really is more focused to work in the complex water around next to in the shelf around the coast. This one really enables us to reduce the chlorophyll overestimations due to the band ratio algorithm, like the one we were using before, and also on the other side extends the range of applicability of the neural network. This is the validation for the basin, and here I'm going to make a point that is important. I'm using the opportunity of having a good part of the oceanographic community of the CMEMS in the Black Sea, is that we're using a rather limited data set for validation. As you will see, these are all data that we were able to source using CDataNet for our satellite data validation. So if you're aware of any data set that could be used, we could use to extend our validation, we would really grateful to and we will really include it in the next documentation for the algorithm. Okay, so as I said before, we will introduce our next step is introduction of the 300-meter OLCI that should be done in the December entry in service, and then we are aiming to introduce the phytoplankton type variables for the in 2022-2021. And here I repeat my request: can you help us in source in-situ data validation, particularly for the phytoplankton type variables? If you're aware of any data set that could be useful, it would be really appreciated. To conclude, I'm showing you the trend anomalies for the Black Sea, how they are in the ocean monitoring indicators in the catalog. So on this side, I have the chlorophyll time series and trend for the Black Sea from this year. So from that should be in the catalog in July. We changed we upgraded the method to apply the trend estimate, so we cannot compare to the previous methods. And overall, we see a decreasing trend of -1.3% per year for the last 22 years. And in terms of the Black Sea chlorophyll anomaly, the average anomaly was being this year compared to the mean values for the previous 20 years is positive. So there is an average anomaly of 0.81, but there is an overall concentric pattern, being that the center of the basin now is showing a positive anomaly, while the outer part of all the shelves are a negative anomaly, with a strong negative anomalies in particular for all the western and northern shelf. And with this one, I conclude, and I thank you for your attention.
Okay, thank you, Vittorio. I see two questions. One is for you and one is for Vinca. We will address first yours so that you are already here. And this is the question: which one of the two available algorithms, OC4Me, you use for chlorophyll A?
No, we don't use OC4Me. OC4Me is the global algorithm for OLCI that is geared towards mainly in open waters, and we don't use that in the Black Sea because we have shown that it's not accurate enough, and that's why we have moved to the two algorithms that are described in my slides, in our quiz, and are works that were published in 2018 and 19.
Okay, thank you. So if we come back to Vinca, there was a question for her. Remember to switch the microphone on, Vinca. And in the meantime, I repeat the question, which is what interpolation?
An optimal interpolation scheme, but I won't get into much more detail, except that you'll find information on it into the docs reference folder, which is available with the Jupyter notebooks or in the user manual. There's two articles in the references which are explaining and giving references, because the optimal interpolation scheme used was from two articles, one from Le Traon and Ogor in 98, and another one from Ducet et al. In 2000. So those are the main seminar articles, but you'll find newer articles within the reference folder, and I encourage you to read them if you're interested into the detail.
Okay, thank you, Vinca. So we can pass to the next presentation, and okay, so Vinca has turned off the microphone. It is fine. So for the next presentation, you will see now which products are available from the In-situ. And the presenter is Veselka Marinova, head of the Ocean Technologies Department of the Institute of Oceanology of the Bulgarian Academy of Sciences. So Veselka, the floor is yours. So you have to turn the microphone on, which is the button on your image.
Hello, everyone.
Okay, perfect.
My name is Veselka Marinova, and I'm coming from Institute of Oceanology, Bulgarian Academy of Sciences, and I'm responsible for the Black Sea component of the Copernicus In-situ tab. I present you in-situ observation products. So, In this presentation, I will focus on in-situ data, in-situ TAC organization, in-situ TAC products, and finally, in-situ TAC improvements. So how can we have a better understanding of the ocean state? The best way to do it is to go in situ with instruments and to measure the current state of the ocean. In situ data collected with observing system is critical for complete understanding of the ocean. In order to monitor the ocean state and respective impact on climate, we have to use a multi-platform approach to collect in-situ data. To do this, we integrate into in-situ Thematic Assembly Center data coming from a wide variety of measurement platforms from research and opportunity vessels, gliders, profiling floats, drifting buoys from moorings, fixed stations, and HF radars, which obtain profiles and time series for temperature, salinity, wave height, sea level, currents, and a lot of other parameters. Copernicus In-situ TAC is coordinated by IFREMER France. It is distributed center organized around 7 oceanographic regions, the Global Ocean, and the 6 Eurogos regional alliances. One of these regions is the Black Sea. Main objectives of in-situ TAC are to collect multi-source, multi-platform data, perform consistent quality control, and distribute it in common format in near real time within 24 hours to the Copernicus Marine Forecasting Center for assimilation into their numerical ocean models, and to supply the Marine Forecasting Center and downstream user with reprocessed 25-50 years products in delay mode. In addition to near real-time products, these delay mode products are useful for model validation or assimilation in ocean reanalysis and climate studies. In-situ TAC service is fully operational since April 2015. Provide open and easy access to in-situ products through CMEMS catalog. The users need to register before downloading the products according to their needs. We are working in strong collaboration with Eurogos and other in-situ data providers, CDataNet, and EMODNet. We are also sharing the same netcdf file formats. The used netcdf format is described in the new Copernicus Marine In-situ Format Manual 1.4 based on ocean state and Argo user manuals. It was released in April 2020. In addition, we have the same FTP structure in all regions. We're using the same real-time quality procedures and quality flagging convention. And finally, we provide 2 products family, near real-time and reprocessed products. Here you can see the general scheme of the in-situ TAC data flow. The data flow within Copernicus Marine In-situ TAC is carried out by 7 regional product units, the production unit assemblies and quality controls in-situ data from national, regional, and international observing system and deliver them to the Copernicus distribution unit where they are made publicly available. distribution unit is operated by another element of CMEMS. On the map here, you can see In-situ Thematic Center in a few numbers in more than 7,000 platforms that are active in real time and 37,000 platforms that are integrating into the OCTAC at more than 300 providers. In the dashboard is shown only 121 providers because only last 30 days period is displayed here on the map. BS.PHY In-situ product provides, as I mentioned before, BS.PHY In-situ production unit provides two products, near real time and reprocessed. The table here summarized the In-situ products family. Sorry. Reprocessed product provided only by Global, and near real-time In-situ product provided by Global and regional production units. For the BS.PHY, we provide only near real-time product. It integrates different variables as temperature and salinity, sea level, wave data, some wave data, biogeochemical data also, and other parameters. Sorry,
Okay.
It's not very good. So, new concept regarding reprocessed In-situ TAC products. Regional temperature and salinity reprocessed products were removed from catalog, and global temperature and salinity reprocessed products take over the regional products. Regarding near real-time product, we continue to distribute global and regional near real-time products, but this product will be constantly updated with the best version of available data in terms of quality and time coverages. In other words, it is a combination of near real-time data when there is no reprocessed data available. Finally, a new acronym for these products will also be introduced. Each region In-situ production unit distributes all its data and metadata in netcdf file on FTP server. To download BS.PHY near real-time product, you first need to register. Once registered, the users can access netcdf file product from In-situ TAC website through the CMEMS web portal FTP service, following the link listed here in pink and blue respectively. For each region, here the Black Sea region, the FTP portal is organized in one product directory, with one dataset directory. Data coming from in-situ platforms are grouped in 3 different directories. The latest directory contains the latest 30 days of data. It contains one directory per day, which is one file per platform per day. It continuously updates every hour. The monthly directory contains the latest 5 years of data. It contains one directory per month, which contains a file per month and per platform. It's updated once a month. The history directory is dedicated to long series of observations. The history, it contains one file per platform and updates once per month. The reference directory in yellow on the chart is dedicated to scientifically reviewed observations, proper calibration, and an error associated to the data. The reference directory organized is identical to the history directory. It is regularly updated, usually one a quarter. For now, this directory is only included in global near real-time datasets such as Argo delayed mode data. Hydrographic calibrated ETD cruises are distributed in this directory. Additionally, there are 3 index files describing the content of latest monthly and history directories. In addition to this, there is a platform index file that register the list of the platforms that are available on the server. These index files are useful for synchronization between the distribution unit and operational users. Here you see a snippet of the index file, latest file for the Black Sea near real-time product. The latest index file describes all the files available in the latest directory. Each index file contains one line per file. Expose the file name for downloading plus some metadata for each filtering. The lines in the index are sorted by file name and time coverage start. Next is shown a fragment of the index platform file. Index platform file is updated daily and contains a list of individual platforms that are available on FTP server. The name convention of the 4 different directories for the dataset includes in the products is as following: regional bigram. BS is the regional bigram, refers to the Black Sea component, file types, data types, platform code. The document specifying the netcdf file format of Copernicus Marine In-situ TAC used to distribute in-situ data and metadata is Copernicus Marine In-situ Format Manual 1.4 and was released in April 2020. And it is based on ocean site netcdf data format. Now the format is more consistent. To guarantee the stability of the format, it will be reviewed every 6 months maximum.
Sorry, Veselka. Just to tell you that you have 1 more minute.
Okay.
Thank you.
Thank you. Under the product name, new rules, under the product new name rules, the name of the BlackSea near real-time product and data sets will be changed. The regional bigram will also be changed. To improve our service, we developed In-situ TAC website, the Copernicus In-situ site, marineinstitute.eu offers an interactive overview of available observation data as well as software tools and explanation on data processes. This site provides quick access to In-situ TAC documentation to monitor the service delivery. We developed key performance indicators. They are monitoring the In-situ TAC activity in terms of daily flowing. You can visualize the data directory in the portal or download them as file in netcdf format. And going to the end, this picture here summarizes the improvements we have achieved. The main objectives of In-situ TAC are two, but we are working to add value to our products. Data quality makes us different. The quality procedures are not applied in other services like eModNet or CDataNet. Extra functions, dashboard, KPIs, smart views, etc. Feedback, and we plan now feedback to providers. Notify the providers about possible features in their stations most of the time before they notice on their own means. Thank you for attention.
Thank you, Veselka. Thank you for this presentation about the In-situ products. There is no specific question about the presentation, so I suggest to proceed. Sorry, there was a question. Is there any data set regarding In-situ SST covering the period 2010-2013?
Yes, we provide time series of sea surface temperature from since I think 2008, and we have data for this period, for this time period.
Okay. Okay. Thank you, Veselka. Please turn the microphone off now that we changed the presenter.
Thank you.
Thank you again. And so, last but not least, is now the turn for the bioproducts, and they will be presented by Luc van den Bulck from the University of Liège. So, Luc, you can turn the microphone on. Okay.
Okay, thank you, Paula. And I'm going to present to you the biogeochemical products from the Copernicus marine systems in the Black Sea. And these products are delivered by the University of Liège in Belgium by my colleagues and myself. So This slide presents to you the why we do this. What is the goal of these products? So in the Black Sea, there's a very important vertical stratification. There are some vertical barriers which prevent vertical movement of different substances, which leads to strong stratification. For example, in the uppermost layers close to the surface, there's oxygen. But then once you go at a certain level, there's no more oxygen. And all the way up to the bottom of the sea, there's no more oxygen. Nutrients have different vertical structures, and with sometimes concentrations at the surface and higher concentrations below, and then again go to zero, etc. So the goal of the biogeochemical models is to represent all the different biogeochemical components in space and time. And when I say in space, I mean in the horizontal and in the vertical. And when I say in time, I mean on a seasonal timescale or even on a daily timescale, but also on an interannual timescale, and see the long-term evolutions. So to perform this task, the tool is two coupled models. The first part of the model, of the coupled models, is the physical model, which you already saw presented by Stefania. So in our case, it's the NEMO model with a horizontal resolution of about 3 kilometers. And the second component in this set of models is the biogeochemical model. In our case, it's called BAMBI, and I will present it in more detail in the next slide. It's a food web model, so it represents the nutrients, the phytoplanktons, the zooplanktons, etc. in the water column, but it also represents what's going on the seafloor. So this is called the benthic model. And the whole system runs at a supercomputing center in Belgium. The model is also requiring data to work. The first part of the data is the atmospheric forcing files, which are provided by ECMWF. Another thing that the model needs is the initial conditions. Also, as Stefania said, for the physics, we need some inputs at the Bosphorus Strait, which is the strait by which the Black Sea waters are exchanged in the Marmara Sea and ultimately in the Mediterranean Sea. And then another very critical forcing for our models is what the rivers are feeding into the sea. And in particular, the Danube River in Romania and Ukraine is putting a lot of nutrients on the northwestern part of the Black Sea, which is very shallow. So this input of nutrients is really determining, is really very important for the results of the biogeochemical models. And so in our case, we as well for the physics and the waves, we provide two model runs. One is called the near real time. It goes on for the 2 last years and up to present plus 10 days, and it's run every day. And the other one is the multi-year product, which is run once, and it goes from 1992 up to 2019 in the present state. And all the results of all these models are provided to the CMEMS, the Copernicus Marine Catalog, and you can access it, of course, on the Copernicus Marine website. For the biogeochemical products, there are 5 data sets. One is the nutrients, so nitrates and phosphates. One is about phytoplankton, so the carbon content of phytoplankton and the chlorophyll content, and the net primary production. One is about oxygen and dissolved oxygen, and one is about the carbonate system and the acidity variables. Some more details about the biogeochemical component of the model. So as I said before, it has 2 compartments. One is the pelagic model, so the one representing the water column, and there are 28 state variables. And the other one concerns the bottom of the sea. The benthic module has 6 variables. The one specificity of the BAMBI model is that it was designed for the Black Sea specifically. So it represents all these processes. If you remember, there's this area here where you transition from a zone with a lot of oxygen and a lot of biological processes going on to another region here deeper below where there's almost nothing going on. And in the transition regions between these two, there are a lot of specific processes going on, like denitrification, nitrification, ammonox reactions, etc. And all these processes are explicitly modeled in the BAMBI model. Thanks to that, and thanks to the sediments and the seafloor model, the BAMBI model is able to run for decades, so maybe 30 or even more than 30 years, without having drifts or other significant problems. So this model, in our case, the model is coupled to a physical model. It's NEMO, but BAMBI has been coupled before to other models or even offline, just by reading the physics from some files. And it's well validated in the literature. This is another diagram showing the different compartments of the biogeochemical model. So you can see the nutrients, the phytoplankton, the zooplankton. There are also some gelatinous, some bacteria, organic matter, both in dissolved and particular states, metals, oxygen-demanding units like iron, and then you have carbon, nitrates, phosphates, and silicates in the sediment, which are labile or semi-labile. So this is related to the easiness or the difficulty for the elements to interact with the water column, or they can be deposited or they can be resuspended. So this was what I had to say about the models, and then this model has, of course, to be validated. You can find extensive documentation about the validation of the model on the CMEMS website in the document which is called QID, so Quality Information Document. The model results are compared to in-situ observations, which was just described by Veselka. And one specific problem of the Black Sea, which was already mentioned before today, is that we had a lot of in-situ measurements in the 70s, the 80s, the 90s, and then there's a gap in the 2000s, 2010s, which was later filled by the Argo floats. So we have now four Argo floats going around in the Black Sea. One problem still in the recent years is that the Argo floats stay in the deeper part of the Black Sea. So we have few measurements on the northwestern shelf, and in particular, we don't have almost no measurements in the Ukrainian and Russian parts of the northwestern shelf. So these are regions where it's difficult to validate the model. Anyway, with the data we have, we still can validate the model. And this is an example of the validation of oxygen. This is the concentration of oxygen as a function of the depth for different months of the year. So for January, February, etc. One plot for each month. In red, this is the results from the model, and in blue, it's the observation by in-situ observations, or be it by Argo or by vessels or by something else. So you could see that the model captures well the higher concentrations in the surface in the winter, lower concentrations in the surface in the summer. This is mainly related to the fact that you can dissolve more oxygen if the water is colder. Then you have this oxygen maximum below the surface, and then the oxygen goes to zero at about 100 to 150 meters depth. Another plot still about oxygen. This is instead of plotting all the available profiles, this is just a monthly mean. And you can again see that the model and the model represents well the situation measured by the in-situ observations. Another interesting thing you can see is the time evolution of these observations. And you can see that the region where there is oxygen, so basically everything above the red line, is getting smaller in time. So in 1992, there was like 140 meters depth. The oxygen was concentrated above 140 meters depth. And now in the most recent years, it's going up, and we are at 120 almost now. I'm sorry, the one is missing here. It's, of course, it's 160, 100. No, it's 60, 80, 100, 120, etc. So this is 140 meters depth, actually. This is another example of a validation for chlorophyll. In this case, we compare the chlorophyll predicted by the model with the one observed by the satellites, and which was presented before by the OCTAC. And we do this for different subregions of the Black Sea. The subregion 1 is the western part of the deep basin in the Black Sea. And this plot is actually for the upcoming version, which will be made available in July of this year. So it's not the plot for the version you can download now. This plot corresponds to the newer version, which will come online in 3 months or 2 months. And you can see that the model can capture very well the chlorophyll concentration on the surface in this region. In the next plot, you see the same thing for region 2, which is again a region in the deep sea, but more to the east of the basin. And again, it's very flattering for the model. And in the next plot, you can see the same thing, but for the coastal region of the northwestern shelf, just in front of the Danube. And this is, of course, a region which is very difficult to simulate because the Danube is bringing a lot of nutrients, and maybe the data we have for the rivers is not always accurate, so it forces some wrong nutriments into the ocean model. And of course, this leads to discrepancies between the chlorophyll in the model and in the satellite observations. But you can still see that overall it's not so bad. For some other variables like pH or alkalinity, we don't have a lot of measurements. And so what we can do then in that case is to compare the general shape of the model results with the general shape of observed results, like a climatology. And in the case of these variables, of course, the model captures well the general shapes, but it doesn't give you day-to-day information about the performance of the model. So if you're interested in these aspects and you go look at the QUID documents, you will see that for some variables we can compare to day-to-day observations, while for other variables it's more like a general validation of the quality of the model. So as I said before, there are 5 data sets in the Copernicus catalog: one for nutriments, which are nitrate and phosphate, one for phytoplankton, one for oxygen and primary production, one for the carbonate system, and one for CO2 variables, which are the surface concentration of CO2 and the flux of CO2 between the ocean and the atmosphere. And you can try to download some of these files or try to plot the contents of some of these files and look at trends in time if you do the Jupyter notebook exercises proposed by Copernicus training. I will finish my presentation by saying something about the upcoming version, so the changes which will be presented to you after July this year. So the major upgrade in the near real-time product is the fact that we will assimilate sea surface chlorophyll observation by satellites. We also do some minor upgrades to the representation of CO2 and to the physical forcing model configuration. And there will be a 2-month period from July to September where you can download the old product or the new product, so you can upgrade your download scripts if you have any. For the multi-year products, we also do a very major change in the next July. The physical forcing model used to be the GARE model, and it will now be replaced with the NEMO model. Also, we will add a new alkalinity model, which was already done in the near real-time product. In the long time series from 1992 to 2019 or 2020, there is no data assimilation or no nudging at all. So the model is running completely freely. And also the model will be run up to present minus 1 year, I think, for the start. So you have a complete continuity between the multi-year and the near real-time products, and you can assemble them and have a unique time series, a single time series from 1992 up to present. So I think that's it. Thank you for your attention all the way to this time of the day.
Thank you. Thank you, Luc. Okay. There is a question about how to access products near a time series of more than 2 years.
If you go on the website, you could download the near real-time series for as long as it's available. I think for now it's still available from 2017, but it will be deleted as on the way as we extend it with time passing. We will start to delete the oldest one because it is redundant with the multi-year time series.
Okay, thank you. I think there is also another. Oh, sorry. You wanted to say something else?
No, that's it. Sorry.
Okay. I see. Okay, there is another question. Do you compare results from your models with those from the JRC modeling toolbox 2, the Black Sea ecosystem model?
Actually, we didn't really compare our models with the results from the GRC models, but in 2019 there was an initiative by GRC to study the impact of the rivers and the discharge of the rivers under different pollution scenarios. And in that exercise, we compared the results with GRC. And I think GRC is now in the process of writing a paper about this. And I guess it will be available very soon.
Okay. So thank you, Luc.
If you allow me, there's a question about the 2-layer flux in the Dardanelles.
Okay.
Maybe I can say something. So we don't model the Dardanelles, which is between the Marmara Sea and the Mediterranean Sea, but we do something for the Bosphorus, which is between the Marmara Sea and the Black Sea. And in that case, the flux, the water flux is indeed a 2-layer flux with water coming in and going out, respectively above and beyond a certain vertical level. And these fluxes are computed based on the conservation of water. So the total water in the Black Sea should be conserved, and based on the sea level in the Black Sea, we can compute this flux. And the salinity of the incoming water is also computed in order to conserve the total amount of salt in the Black Sea.
Okay. Thank you, Luc, again for this last presentation. And so we have arrived at the end of this morning session, actually morning and part of the afternoon. So I thank all the presenters and all of you for attending. Now it starts your own work at your place, at your home. So you will be prompted with all the material prepared by the trainers about these products. So you will have the opportunity to reflect more on all the information you have received this morning, and to exercise with the products. To ask questions, in case questions were not answered now, you can post it in the chat platform that will be also available for you to interact with the trainers. So we wish you a lot of work during the next 2 weeks. Do not forget to reply to the feedback questionnaire. And I pass the floor to Fabrice if he wants to add anything.
No, you already said everything. Thank you for your attention, and thank you to all the trainers and speakers for this first online training session.
Okay, so we will reconvene in person at the beginning of June, and in the meantime, just interact with us by all the tools that are available for you. So thank you, and have a nice afternoon.
Thank you. Bye. Thank you, Paola.
Thank you. Bye.